Okay, today we're going to learn about operating point. And what is that? So let's take this circuit here. Let's see what will happen. Well, if we assume this transistor is in the active mode, that means there's a voltage drop right here of what? 0.7 volts. Let me get a red marker and write 0.7 volts there. Let me get a calculator here. So there'll be a 0.7 volts right here. If we assume this is, if we're doing first approximation, then this voltage is what? 0. Okay? So now to calculate I sub B is going to equal to 15 minus 0.7 over 500K. That's using second approximation. In second approximation, that voltage is 0.7. First approximation, if we use first approximation, that's second approximation. First approximation, I sub B will be what? 15 minus 0 over 500K. Maybe I'll use the first approximation just to make the math quicker. So 15 minus 0 is 15 divided by 5. That's 3. Where's my calculator? Remember, this is 500K. I'm not just writing the K here. So that should be about 30. 15 divided, oh, turn it on there, it's clear. 15 divided by 500K, e to the third. And it's 30 milliamps, or microamps, not milli. And if we assume this transistor has a beta of 100, that means I sub C is going to be what? 100 times I sub B. And 100 times 30 micro is 3 milliamp. Now that's 3 milliamp. Let's find out what VCE is. So the voltage between C and E right here. If you look at that circuit, it looks like this. There's 15 volts. There's a resistor of 3K. And there's a voltage here of between this and ground. That's ground here. So it's going to be, VCE is going to be what? It's going to be 15 minus, I sub C is coming down, I sub C times 3K. So what's VCE equal to? There we go. 15 minus 3K, that's 3,000, times I sub C, which is 3 milliamp, 0.03, I think, or 0.3. VC is equal to 6 volts. So right now, if you're looking at this transistor, if this is like 1 milliamp for I sub C, 2 milliamp, 3 milliamp, 4 milliamp, 5 milliamps, and this is, we'll put some voltages down here of like 6 somewhere here. We're working at this point. That's where we are, right there. That's the Q point. That's when the voltage VCE is what? It's actually 6 volts, and when the current is equal to, oh, it's supposed to be 3 milliamp, not 5. So 3 milliamp will be right here. We're right there. VC equals 6, and I sub C equals 3 milliamp. Now, if we take another value for beta, let's change beta, for example. Let's assume this transistor has a beta of a value of 75. Well, this doesn't change here. So if beta, which is, by the way, HFE, equals 75, I sub B is still the same. Still 30 microamp But now I sub C is going to be 75 times 30 microamp. And let's see what that value is. 75 times 30 e to the negative 6. And that's 2.25 milliamp. Well, if that's 2.25 milliamp, then what is VCE? Again, VCE from that picture here is going to equal to 15 minus I sub C times what? 3K. So it's going to be 15 minus, what's I sub C? 2.25 milliamp times 3,000, or 3K. The 3K and the milliamp will cancel each other out. So we'll have 15 minus 2.25 times 3. And that will give me 8.25 volts. So if I was to put another point on my graph now, that would be the 8.25 somewhere here. And the current is going to be 2.25. That's going to be somewhere right there. There's the 2, that's 2.25. And if you connect these points together, if we have a ruler here, like this one, now my graph is not ready to scale here. That will be the line, actually, you want to operate on it. That's Q here, and that's Q1, and you can put a different value for Q. You're going to see it's a straight line. Now, how do you get that line? If you don't want to go through these calculations, there's a quicker way to get that line. And I'll show you what that quicker way to get that line instead of picking 10, 12 values. Going back to the circuit here, 500K, 15 volts, $3K, 15 volts. Now, let's make a couple assumptions here. If this transistor is off, what's going to happen? If that transistor is off, that means I sub C equals 0, which means VCE equals 15 volts. And what about if the transistor is really, we call it saturation? If it's in saturation, what does that mean? Let's assume this voltage VCE is 0. It's not really 0, but let's assume it's 0. Then what is the current I sub C? It's going to be 15 minus 0 over 3K, which is what? 5 milliamp. So if you were to find the line now, that load line, you know how we had these currents looking like this, different value of I sub B? So you find where the 5 milliamp on I sub C here, and this is here VCE, and you find the 15 volts here, and you connect the two lines together, and that's your load line. So you tell me what voltage you're going to be at, and I'll tell you what your current is going to be. Now this point is called the cutoff here. That's the cutoff point. And this point here is called what? The saturation point. What does that mean, the cutoff? The cutoff means transistor is not even working. So what about the saturation? Well, we know that I sub C equals beta times I sub B. When you're in saturation there, that equation is not true. I sub C is going to be a different value. Does not fit that criteria. So you always want to work right there between them so you can stay in the active mode. So that's the key to that, actually, that graph there. So that's one of the topics I want to talk about today, the operating point, or the Q point, we call that. And now, if we take this circuit and reverse now, or take that resistor and move it down here, what will happen? Instead of the resistor being here, let's put it down here. If we do that, this is called emitter-bias circuit. So let me draw a circuit there. I'll just use different numbers so we're not bored. Are you bored yet? Hopefully not. Let's say we had a 2.2K resistor here. This is not emitter bias yet, because notice where that resistor is. This is 1K, and this is 15 volts. To make the circuit emitter bias, I'm going to move that one down to here. So if I do that, my circuit will look like this. And how does that change the solution? How would that change the current I sub B and I sub C? Now remember, let's assume beta here is 100 for this. So for this example, beta is going to, I sub B is going to be what? Is going to be 5 minus the 0.7 if we use second approximation over 2.2K. Let me get my calculator here. 5 minus 0.7 divided by 2.2 EE to the power 3. And my calculator says I sub B is going to be 1.95 microamp. What's I sub C going to be? Beta I sub B. So multiply that by 100. And that's 0.195 milliamp. That's for the top circuit. Now what about for this one? So let's look and see. This is the 0.7. This is I sub E coming down. If you do Kirchhoff current law, says sum of the voltage in a closed loop is what? 0. So we have 5 minus 0.7 plus. Now some of you might use this as minus, this is plus. If you're going to do that, that's fine. It really doesn't matter. If you like to enter the minus sign with the minus, the plus with the plus. then this will be a plus 2.2K times I sub E is equal to 0. Can I get I sub E now? What's I sub E is going to equal to? It's going to equal to 4.3 divided by 2.2K. Which is 1.95 milliamp. Can we figure what I sub B and I sub C now? Excuse me. We know I sub E equals I sub B plus I sub C. And what's I sub C? Beta times I sub B. So now we have what? 1.95 milliamp equals 101 times I sub B. And what is I sub B now? 1.95 divided by 101, which is 19.3. Let's make sure I divide it correctly here. 1.95, sometimes I get distracted, divided by 101. And that number is what? 0.193 microamp. Do I know what I sub C is? It's beta times I sub B. Beta is 100. 100 times that number, which is what? Times 100. And that will make it 1.93 milliamp. Can I find VCE now? So what's VCE going to be? Well, here, if you do Kirchhoff voltage law, VCE equals what? So let's look at that circuit. Let's look at this side here. Here's what we have. We have a 15 volts on the top. We have 1K here. We have a voltage here of VCE. And we have a resistor here of 2.2K. Keep in mind that the current here, where's my red marker? The current here is I sub E, which is 1.95 milliamp. And the current through this is 1.93 milliamp. So what's the voltage right here is going to be? Ohm's law says this voltage here is 1K times that. 1.93 volts. This voltage will be what? 2.2K times that number. It's 4.29. You okay? So now, can we get VCE? 15 is equal to what? 1.93 volts, that's the drop right here, plus the voltage here, plus the drop right here, which is 4.29. Can we get what VCE equal to? 15 minus 1.93 minus 4.29, and that's equal 8.78 volts. So that changes the whole problem. Here VCE would have been much larger. because the current is what? 0.195. Down there in this circuit here, in the original one, this is going to be VCE. I don't have space to write that here. Equals 15 minus 1K times I sub C. So that would be what? 15 minus 1 times 0.195, which is 0.195, and that's 14.8. And look what VCE right here is. See that one? It's much smaller. Now, let's take another one here, and let's combine this chapter with another one. Let's put an LED with this. So let's take this one, which is 15 volts, and let's put a switch here. And this is 15K. And now here I'm going to put an LED. $1.5K, and let's put a 15 here. And again, this LED lights here as the current goes through it. There's the light, emitting the light. And let's assume this LED has a voltage here of 2 volts when it's on. So let's analyze this. When the switch is open, there's nothing going through this. So this is really off. So let's say close at t equals to 0 here. For t less than 0, the switch is off. That means I sub B is 0. The transistor is off. I sub C is 0. LED is off. Now, what about when t is bigger than 0? What's going to happen? When t is bigger than 0, this switch will close. And I think I said 15 here. This is here 15K. And maybe I'll use the first approximation, just to make the math easy. I don't have to use the first approximation. You know what? I'll stick with the second approximation. What's this voltage right here? 0.7. So what's I sub B? 15 minus 0.7 over 15K. $14.3 divided by 15, which is what? 95. 0.95 milliamp. Let's assume beta is 100 just to make the math easy. That means I sub C is going to be what? 100 times I sub B, which is 9.95, I think, 95 milliamp. I can't think now. So VCE, what's VCE? Here's the LED. Current's going to flow through that. The LED is going to be on. This is 1.5K. This is 15. So if we travel this way, 15 equals what? 1.5K times I sub C plus the voltage here, which is what? 2 volts plus VCE. $15 equals 1.5 times I sub C. What's I sub C? 95 milli. 1.5 times 95 is that milli or micro here? Let's see. So you end up with some big number. You have 142 plus the 2 plus the VCE. That tells me VCE is negative. That doesn't make any sense. Negative. So what does that mean? That means what? That means we're in saturation. You can't use I sub C equals beta times I sub B. We are in saturation. So it really doesn't matter what beta is. So now let's change it around there. Let's move that resistor down here and use different values. So let's take another 1 here, 15, and again, emitter bias now. Let's put a 1.5 kilo ohm here. I'm not putting a resistor up there. 15 volts. So now again, when the switch is open like this, the transistor is off. When the switch closes at t equals to 0, the transistor is on. So we're going to have 15 equals 0.7 plus 1.5 K I sub E. Beta equals 100 again. This is the same LED one, 2 volts here. So 15 minus 0.7. What's 15 minus 0.7? 14.3 equals 1.5 K times I sub E. Can we get I sub E? 14.3 divided by 1.5 K, it's 9.5 milliamp. Now, I sub C is going to be roughly what I sub E is. Give and take, maybe 0.1, it might be 9.48. So it's really not going to make much of a difference. And it really doesn't matter here because I didn't put a resistor there. So if we look actually what VCE is going to be, here we go. KVL right here, 15 equals the 2 volts here plus VCE plus 1.5 K times I sub E. 15 equals 2 plus VCE plus 1.5 K times ICB, that's a milli, the K's and milli cancel each other out, 9.5 times 1.5, and that's what? 14.25. 15 equals what? 14.45 VCE, and what's VCE? 0.55. Notice the current here, it's actually is independent of the LED voltage. That current here is going to be whatever beta, almost that current here. Doesn't matter what that voltage there is. So this is, we can say the LED voltage drop has no effect on the current. It really doesn't change the current. ICB is going to be the same. It's only going to change what VCE is. You almost at this point, notice that number is so small, almost at saturation. For a silicon transistor, Si transistor, for saturation, VCE is almost 0.2 volts. So you're not that far from it. If you go back to the first example we drew here, you're working right there at the edge of that, somewhere right there. VCE is very small.